from last time? The homework is due on Wednesday. Upload that to Blackboard. I've already got it up there, so scan it with the upload to Blackboard. I've already posted the homework problems for today, so I don't have the answers to homework 1C yet. A review of Fourier transform stuff. Problems aren't simple. Deal with some complex numbers. Some cases, watch out for any time you multiply by a cosine or a sine or an exponential, that you can use the modulation property. So I know there's one problem where it's like one comp of a cosine or something. If you model that as actually a cosine times a rect, which it is, then just apply the modulation property to the Fourier transform of the rect. It's a couple of lines. If you evaluate Fourier transform directly, you can get there, but then it's like 2 pages ago. And that's good. It's good to go through that exercise. But those are like multiplying by cosine, sine, complex exponential, complex sinusoid. Try to apply that modulation property. Then there you got a product that actually becomes a convolution, but in the Fourier transform domain, the Fourier transform of cosine is a pair of exponentials, or the complex sinusoid is a pair of impulses, or the complex sinusoid becomes just an impulse. And convolution of an impulse is just shifts the transform. So it's good to, you may want to try and tackle that both ways. You probably won't, but just to see how much easier with the little insight, the problem actually is much easier. So a couple of, I'm going to talk about the relationship between pulse width and bandwidth today. And then we'll also review the Dirac delta function or the continuous time impulse. So first, let's talk about bandwidth. And again, bandwidth will be the width of the Fourier transform of the signal. Bandwidth will be really important to us in this course. It determines how many channels we can have within an allocated spectrum. You have to space them so that they don't overlap. But given a frequency range from 1,000 kilohertz up to 2,000 kilohertz, how many channels we can put in that frequency range depends on the width of each channel or the bandwidth. So that the pulse rect T of T has, G of T has a magnitude spectrum. This is just the absolute value of the Fourier transform. The Fourier transform is simply AT sinc of FT. But we determine the bandwidth from the magnitude spectrum. And so what that looks like is it's really just the absolute value of a sinc function. And it'll be 0 when we're in the Fourier transform domain, or working on the f-axis now. So this will be, remember, sinc of ft is sine of pi ft over pi ft. So it'll be 0 when sine of pi ft is 0. That's when the ft product is equal to 1. The sine of pi is 0. Or when ft is equal to 2, sine of 2 pi is 0. Or ft is equal to 3, sine of 3 pi is 0. So sinc is 0 when its argument is integer value. In other words, when ft is equal to 1, that occurs when f is equal to 1 over t, or 2 over t, because with f equal to 2 over t times t, that's 2, or 3 over t, or minus 1 over t, minus 2 over t, and so on and so forth. Now, we're taking a look at a modulated pulse. The n of t is a over t cosine of 2 pi c of t, then remember what we get is 1/2 the spectrum shifted to the left by fc and then shifted to the right by fc. So what we get here is the Sine function f minus fc times t plus sin of f plus fc minus t. Now, if fc is small, there's some interaction between these Sine functions. Okay? But if fc is fairly large, these things are fairly far apart, and we take the absolute value of them independently. And in that case, if fc is much, much larger than 1 over t, then we get a picture that looks like this. And this would be fc, this would be minus fc. This would be fc plus 1 over t, fc minus 1 over t, and this is in the f. So this is, one of the key points here is, and there's a factor, one of the key points here is that when you modulate, this would be called a baseband signal, a low frequency signal. And by modulation, the simplest form of modulation is just multiplying by cosine. It translates the spectrum to a much higher frequency, in this case, around fc. And fc is what we call the carrier frequency of this particular signal. So this is, again, the simplest form of modulation. It's a form of amplitude modulation. So we've got a whole chapter devoted to amplitude modulation. It's not AM radio, but it's pretty close to AM radio. It is a useful form of modulation. But and then here, the scale here would be, for audio frequencies, maximum audio frequency, might be 20 kilohertz or something. The carrier frequencies that we use and on your AM radio, it's like 660 kilohertz, and then up to 1440 kilohertz, 1.4 megahertz. So this is in the megahertz range compared to 20 kilohertz. So 500 times further out. So fc is really large typically compared to 1 over t and our modulation problem. So it really isn't to be on the same scale to be drawn much further to the right than to the left. But what I really want to talk about now is what is the bandwidth. Now, I typically use this as abbreviation for bandwidth, the bandwidth of Dm of t. Well, it's not well defined, the width of this thing, right? And let me tell you now, and you guys will miss this, I know, the bandwidth is the width of the positive frequency. So even for the width of this thing, let's say it's the null to null width. Okay, that would be one. That's the simplest. Null to null. That's what it's called. 0 to 0. Null is another one term for 0. Engineers, we've got to have our own code for everything, right? To exclude outsiders. So instead of saying 0 to 0, we say null to null bandwidth. That's the convention. So what would be this width? FT plus 1 over t minus FC minus 1 over t, 2 over t, right? 2 over capital T would be the width. And that's this whole pump. That's that whole width. Then we could argue, well, it's really wider than that because it includes these other side lobes. And it does. Now, what's the width of the baseband signal? The null to null. Well, the null to null width, I guess you could still argue is 2t. But when we talk about bandwidth, we really talk about the range of positive frequencies. So the bandwidth of this baseband signal is actually 1 over t. It goes from 0 to 1 over t. You don't include the negative frequencies. Like over here, you ignore the negative frequencies. And I talked just about the positive frequencies. Question? So that would be one width. Another one would be the 3dB bandwidth. Let me call, sorry. Wn is 2 over t, just so I keep these different apart. W is 3dB. And I'm not going to calculate this, but this is where the width where this thing is down 1 over the square root of 2 from the peak. That's the 3dB bandwidth. So this bandwidth this width is going to be narrower than the null to null. So you can calculate that on that formula. Turns out to be 0.430 t or 0.816 t. It's smaller than the null to null. We can also talk about the RMS bandwidth. I'm not even going to give you the definition for that, but the RMS bandwidth turns out to be a little broader, 3.18 than either of these two. Generally, we'll talk about the null to null bandwidth just because that's the easiest to look at from the spectrum. But the point I want to make now is that all of these bandwidths, they're inversely proportional to t. So what that means is as my rep pulse gets narrower, as t gets smaller, and capital T is the width of this rectangular pulse in the time domain. As that gets smaller, what happens to my bandwidth? Now the bandwidth gets larger. The extreme case of that is as this becomes an impulse. Remember the Fourier transform of impulse is just a constant. We have infinite bandwidth. So that's the important thing. Narrow pulses take up a lot of bandwidth. Short duration signals take up a lot of bandwidth. We'll see this in digital data communications. As you're trying to send bits at a very high rate of speed, then that means you have to have short pulses. That means you need a lot of bandwidth in order to transmit binary data at a very high rate of speed. Another way that this is often mentioned, if I take the pulse duration t times any one of these bandwidths, I'm going to get a constant, right? T times this one is 2, T times this one is 0.886, T times this one is 3.183. So, and this is true, I've used the rectangular pulse here, but this is true for like an exponential pulse. If we look at just a hump of a sine wave, you get the same relationship, where the time bandwidth product is a constant. That's really true regardless of the pulse series. So just kind of keep that in mind. The smaller the duration, the shorter the pulse, the wider the spectrum. Um, the direct delta function, or just the delta function, or just the impulse function, or continuous time impulse function. Again, it's something they typically don't introduce in your calculus classes. You know, but it turns out to be really useful in engineering. It's not a physical signal that we can generate in the lab. You know, we can approximate it with a high amplitude, short duration pulse. But we can't really, you know, it really has no duration and it's infinite amplitude. You know, it's a mathematical concept. We define it to be actually the derivative of a unit step, which we can generate in the lab, unit step. But it's really useful to us in our study of electrical systems. It's actually defined by two properties. It's equal to 0 everywhere except where it's located, where it's actually infinite, but we don't say it's infinite. Instead, the other property is if I integrate over the impulse, that interval is equal to 1, or in other words, it has unit area. It has area of 1. So generally, you know, sketch it like this, and the time domain. And the 1 I put next to it is not the amplitude of the signal, it's actually the area, or sometimes it's called the weight of the impulse. Delta t minus 2 would be an arrow located at t equal to 2. And this integral from minus infinity to infinity, you know, this thing is 0 everywhere except right at 0. I can actually integrate from, change my limits here from minus 1/2 to plus 1/2 and still get 1. Or minus 0.0001 to plus 0.0001. Or just minus 0 to plus 0. Because it has infinitesimal width. You know, minus 0 is just right below 0. 0 plus is just right above 0. So, but if I integrate from 1 to 2, what would I get? 0, because that interval doesn't contain the impulse. And similarly, if it's located at 2, if I integrate from 3 to 4, I would get 1. But if it's located at 2 and I integrate from 10 to 20, I get 0, because the interval doesn't contain the impulse. A couple of properties you can derive from the definition. F of t delta t minus t0 is equal to f of t0 delta t minus t0. This is called the multiplication problem. For some reason, this is so confusing to students in pre-10 and probably worse than you. So, you know, it says, you know, I get some function of time, and I multiply it by, in this case, an impulse. Then the result is another impulse located at the same spot, but with a different weight. The weight is the function evaluated at that point, at the location of the impulse. And it's 0 everywhere else. The product of the time domain function and an impulse is just an impulse. It's 0 everywhere except at the location of the impulse, because this is 0 everywhere except at the location of the impulse. So the product of these two is 0 everywhere. So the only thing it does is it modifies the area or the weight of the impulse. And then another property, property 2, is what's called the sampling property of the delta t T minus T0 dt is equal to f of T0. This is called the sampling property. It follows directly from that multiplication property because this product is f of T0 delta T minus T0. F of T0 is a constant. Right? It's the function evaluated at a particular point in time. So I can just pull the f of T0 outside my integral. My integration over an impulse is 1, so I'm just left with that constant value. So this is called the sampling property of the impulse. We also have the derivative of the unit step. We define that to be the impulse. I think typically in your calculus class, the unit step is 0 for all t less than 0, so the derivative of 0 is 0. It's equal to 1 for all t greater than 0, unit step. So the derivative of 1 is also 0. And then in calculus, it goes from 0 to 1 at the origin. Typically in calculus, it's a derivative is undefined, but perhaps they would say it's infinite at the origin. I don't know. Remember what you used? It says undefined at the origin or infinite. We actually define it to be a new function. That's this mathematical concept. The derivative of the unit step is the impulse. And then similarly, this, I call this the running integral. It would be the output of an integrator circuit. And it's a little bit, you have to think about what's going on here. It's a function of the limit here. Right? So if I draw on my tau axis, this is delta tau. I'm integrating from minus infinity to t. As long as t is less than 0, I integrate over nothing, I get 0. But as soon as t gets to be greater than 0, I get 1. So the result of this thing is it's something that's 0 for t less than 0, but it's 1 for t greater than 0. That's the unit step. So this is called a running integral. It's a function of the upper limit. It has some really interesting properties with regard to system theory, study of linear systems. It's interesting what it does with regard to convolution. Involve anything with delta t, and get just that thing. In the Fourier transform domain, I think we've already talked about the Fourier transform of an impulse. This would become a product of exeta times Fourier transform of delta t is 1. So in Fourier transform, this convolution would become a product. We would just get exeta. Take the inverse transform, we get x of t. So in the Fourier transform domain, this left-hand side just becomes x of f times 1 or x of f, and that follows immediately. And then this is just a shifting function. Again, Fourier transform convolution becomes a product. The Fourier transform of this is just that exponential. But multiplying in the frequency domain by an exponential, this corresponds to a time shift in the time domain. So we need to prove that using our Fourier transform properties as well. We will also be dealing with, here I talk about primarily impulses in the time domain. We'll also be dealing with impulses in the frequency domain. The Fourier transform of a cosine is a pair of impulses. located at the plus and minus frequencies of the sine wave. I'll try to talk a little bit about what is negative frequency. That's often a confusing concept, but I'll try to work that into a lecture, a little brief talk on what negative frequency is and what that means. For us, you can almost ignore it. It's important when you're dealing with complex sinusoids. But like cosine of minus omega 0 t is equal to cosine of plus omega 0 t, right? So we work with real signals, we could almost do without negative frequencies. Sine of minus omega 0 t is equal to minus sine omega 0 t. So you could translate those negative frequencies really into positive frequencies. But it is a useful concept when we're dealing with complex sinusoids. Because I can't simplify e to the minus j omega 0 t. I can't write that in terms of e to the plus j omega 0 t. Throwing a minus on it. Okay. Some other properties. So we talk about delta t becoming 1. Well, it's easy to use the inverse Fourier transform to show that delta f, the inverse transform of delta f, an impulse at f equal to 0 comes back as just a constant 1, which we would classify as, if this were a voltage in time, we say it's a DC voltage. So the DC voltage of 12 will transform as 12 delta f. That's we talk about zero frequency as corresponding to DC. Certainly that's true when you think about a cosine. Like cosine 2 pi ft, if f is 0, cosine of 0 is 1. So we think about a frequency of 0 as being DC. The complex sinusoid. So this is the Fourier transform of e to the j 2 pi f c of t. That just becomes delta f minus f c. I think we already had looked at this Fourier transform. F minus f c. E to the j 2 pi f c of t is equal to delta f minus f c. So, and we won't work too often with these complex signals in time, but occasionally they are useful. And sinusoids, so cosine 2 pi f c of t transforms as, I can write that using Euler's formula as e to the j 2 pi f c of t plus 1/2 e to the minus j, here, 2 pi minus j 2 pi f c of t. So the Fourier transform becomes an impulse located at plus t and another impulse located at delta f minus f. And we get a similar result for the sinusoid. 3 other properties or relationships, and then we'll look at it. What's called the signum function, or also sine function. So it looks like this. It's equal to 1 for t greater than 1. It's equal to minus 1 for t less than 1. So And we use that notation, STN, or the sine of t. It's simply equal to 1 if t is positive, it's equal to minus 1 if t is negative. So the signum function has Fourier transform of 1 over j 2 pi f. Now the signum function is related to the unit step, right? If I double the unit step and subtracted 1, I get the signum function. We could write this is 2 u of t minus 1. Because 2 u of t would be 0, all t less than 0 would be 2 for all positive t. But if I subtract 1 everywhere, back there with 0 now be minus 1. And it's a positive 2 u of t can be equal to 2, subtract 1 would be 1. So signum of t is equal to 2 u of t minus 1. So I could actually solve that for u of t. Now that I've got the Fourier transform of signum of t, I can then get the Fourier transform of the unit step. U of t transforms as 1 over j 2 pi f plus 1/2 over f. U of t is 1/2 signum of t plus 1. Right, solving that for u of t. And so the Fourier transform, because of linearity, is going to be 1/2 of this, signum function is just 1 over j pi f, not 1 over j 2 pi f. This is always 1/2 of that is 1 over j 2 pi f. And then 1/2 of 1, the constant becomes 1/2 delta f. And the final property here is integration. Y of t is minus infinity t. So if I define, this would be again the output of a circuit we call the integrator. Define the output of this to be y of t. This is equal to g of t involved with the unit step activity. So we show that y of f is equal to 1 over j 2 pi f g of f plus 1/2. There's an impulse at f equal to 0 if g of t has a DC part. If g of t has a DC offset. Okay, let's look at an example of Fourier transform. Now, there's certainly a number of different ways we could do this. I'm going to give you a few minutes. The first way we're going to tackle this is think about this as cosine t pi f t of t times cosine of 2 pi f t of t. Now, what does that multiplication become in the frequency domain? Convolution. Normally, we try to avoid convolution, unless we're dealing with convolution of impulses. But cosine pi of c becomes a pair of impulses. Okay, so see if you can figure out what that convolution is. I'll give you 2 minutes to work on that. So find g of f. trick is keeping track of all the impulses here, right? When you use this approach. This is 1/2 delta F plus Fc plus delta F minus Fc. And then convolved with 1/2 delta F plus Fc plus delta F minus Fc. So we can pull out, we've got really 4 different convolutions to go through here, so we can just use the FOIL method just like when we're multiplying. So convolve the first two, 1/4. What's delta F plus Fc convolved with delta F plus Fc? Maybe a little tricky, when we have x of t involved with delta t minus t0, the same is x of t minus t0. X of t minus t1 involved with delta t minus t0 is x of t minus t1, but then with an additional delay. Right? I would actually substitute t minus t0 in for t, so this would be t minus t0 minus t1. I wrote that in the way. So delta t minus t1 involved with delta t minus t0. Now I'm just replacing x with delta. So it would be delta t minus t1 minus t0. I just add the delays. So here I've got t minus t0, delta t minus t0 involved with delta t minus t1. I got t minus t0 minus t1. So here I get, working the frequency domain, I'll have F plus Fc plus Fc. So it's going to be F plus 2Fc. Okay. This is the first then do the outer. What's delta F plus Fc involved with delta F minus Fc? Delta F. This would correspond to a sinusoidal or complex sinusoidal component at 2Fc plus the frequency. This corresponds to a frequency of 0 or DC term. The inner terms, what do I get there? These two. Delta F again. And then finally, the last terms, delta F minus 2Fc. So what I'll have is I've got delta F plus delta F, that's 2 delta F. I'll have 1/2 delta F plus 1/4 delta F plus 2Fc plus 1/4 delta F minus 2Fc. That is the result. And I don't think that's simplifies me further. Let's look at it a different way using a trig identity. You can derive all these trig identities from Euler's formula, but this tends to be probably the most useful trig identity we'll use this semester. Use it enough that it's worth memorizing. Cosine A, cosine B is 1/2 cosine of the difference plus 1/2 cosine of the sum of its tangents. So this is cosine of A minus B plus 1/2 cosine of A plus B. So T of T cosine of 2 pi f c t squared Here my A and B are the same. That's cosine of 2 pi f c of t, times cosine of 2 pi f c of t. So I can apply these, but A and B are equal. So what's this term become? 1 half cosine of 0, cosine of 0 is 1, plus 1 half cosine of, I'm going to write it 2 pi 2fc. Really, you could write that as 4 pi fc of t. Well, let's take the Fourier transform of this. What's the Fourier transform of 1 half? That's 1 half delta f. And the Fourier transform of cosine of 2fc of t, that's an impulse located at 2fc and minus 2fc. Actually, the Fourier transform includes this half term. I've got another half here, so this is going to become 1/4 delta f plus 2fc plus 1/4 delta f minus 2fc. Hopefully I got the same result. There's one other way to look at this that kind of want to bring in a graphical approach. So anytime I have x of t multiplied by cosine of 2 pi f c of t, then this is the modulation problem. You can get it directly from it becomes 1 half x of f minus fc plus 1 half x of f plus fc. But I could look at this as x of f involved with 1 half delta f minus fc plus delta plus fc. So let's say x of f looks like this. So this is maybe the baseband spectrum. And then this thing, this part is an impulse at fc equal to 1 half. That part is an impulse at minus fc equal to 1 half. So, and now I'm convolving these two things. What happens when I convolve with an impulse? A shifted impulse. It just shifts the function. So graphically, what the result would be, let's say this has height of A, to have the same thing shifted at minus fc, same thing at plus fc. It would actually be A over 2, A over 2. And I could actually write this as 1 half x of f, minus fc, the thing shifted to the right, plus 1 half x of f plus fc, shifted to the left. So this is another way to think about multiplying by cosine. I take the Fourier transform of the baseband signal, shift it to the right, and then add to that the spectrum shifting to the left by fc. This is a good way to kind of think about what this property does. Now let's go back. What we actually had, again, this gets a little complicated. I had one cosine multiplying another. So somewhere I did that. This pair of impulses convolve with this pair of impulses. But instead of physically carrying out those convolutions, think of it just as what do we get if I take one spectrum, shift it to the right by fc, then add to that same spectrum, shift it to the left by fc. Then I got to throw in a factor of 1 half. Okay, so I take this, shift it to the right by fc. Where's this one going to go if I shift it to the right by fc? Where's this impulse going to?
Zero.
Yeah, it's going to be 0. And it would actually have a height of 1/4, 1/2, and then the other one. Where's this one going to be? 2FC. And it would have a height of 1/4. Now I add to that this same spectrum shifted to the left by FC. So shift this one to the left by FC. Where's it going to be? So minus FC shifted to the left. It's going to be minus 2FC. And we have a height of 1/4. Where's this one going to be? If I shift it to the left by FC. If that FC shifted to the left, it's going to be 0. Same location of this. It also has a height of 1/4. A quarter plus a quarter. I got two of these located in the same spot. So it'll be a half. If you were to write down the corresponding mathematical expression for this, it would be 1/2 delta F, that impulse at the origin, plus 1/4 delta F minus 2FC, plus 1/4 delta F plus 2FC. Which is the same result we got in a couple different ways. Okay, this is just kind of a graphical convolution with using impulses. And then a number of different ways. We used to say determine when you skin a cat, but I don't think PETA allows us to use that terminology any longer, so I don't know if you guys ever grew up with that expression. A number of different ways to compute Fourier transform. Do it correctly, all roads lead to Rome. It's probably still safe to say that. So we get to the same end point, regardless of the method. But, you know, it will be time saving to think about anytime you see multiplying by cosine, it's shifting the spectrum to the left by FC, shifting